All right, let's jump right into a really cool little puzzle that popped up on a linear algebra exam. It's all about a matrix that, well, it disappears. Let's get into it. Okay, so here's the core question we're tackling today. You've got one matrix that, poof, disappears if you multiply it by itself enough times. Then you've got another matrix that, well, it gets along with the first one. So the big puzzle is, what happens when you multiply them together? Does the disappearing act still work? All right, first things first. To get to the bottom of this, we need to know the rules of the game. So let's meet our two main characters, Matrix A and Matrix C.
So our first player is Matrix A, and it has this really cool property. It's called nilpotent. It's a bit of a mouthful, I know, but the idea is actually super simple. You take this matrix and you multiply it by itself over and over again, and after a certain number of times, say k times, poof, it turns into the zero matrix. It literally just vanishes.
And then we have Matrix C. Now, C's relationship with A is the real game changer here. They commute. You know, with matrices, order usually matters a ton, right? AB is almost never the same as BA. But for our guys, A and C, it doesn't matter. AC is exactly the same as CA. They just get along. And trust me, that friendly little property is the secret key to this whole puzzle. So let's talk about the power of commuting. Because this isn't just some random fun fact. This is what unlocks the key to the entire thing. Okay, here it is. This is the superpower. Because A and C commute, and only because they commute, we get to use this special rule. You see how we can just distribute that exponent m to both A and C? That's something you are absolutely not allowed to do with most matrices. It's like having a VIP pass in the world of linear algebra. You might be wondering, okay, but how does that actually work? Well, we don't need a super formal proof. Let's just test it out for a simple case, like when m equals 2. So AC squared is just AC times AC. Now here's the magic trick. See those two matrices in the middle, C and A? We can just swap them because they commute. So CA becomes AC. And once you do that, you just group the A's together and the C's together, and there you have it. A squared times C squared. See? It works beautifully. Okay, we've got our players, we've got our secret weapon. It is time for the proof, the moment of truth. Let's put all these pieces together and solve this thing once and for all. So here's our goal, plain and simple. We need to prove that if we take the product AC and raise it to that same power K, it also becomes the zero matrix. The big question is, does A's vanishing act get passed down to the product? And how are we going to do that? Well, we're going to use our special tool. We just proved that because our matrices commute, we can totally rewrite AC to the power of K like this, A to the K times C to the K. Now let's pull in that first piece of information we were given. Remember, we were told right from the start that A is nilpotent. What does that mean? It means we know, for a fact, that A raised to the power of K is the zero matrix. And here it is, the final move. We just swap out that A to the K with the zero matrix. So now we have the zero matrix times C to the K. And what happens when you multiply anything by the zero matrix? The whole thing just collapses. It becomes zero. And bam! That's it! We did it!
And there you have it. That's our proof. In Hebrew, you'd write mimshal, which is the equivalent of the Latin QED. It just means that which was to be shown. We've shown that the product AC is also nilpotent. Puzzle solved.
Okay, that was a pretty neat proof, but you might be thinking, so what? Why does this little abstract puzzle even matter? Well, let's talk about what it all really means. The big takeaway here is that this isn't just some clever party trick. It's a really fundamental idea about how properties in math get passed along. Think about it. The disappearing property, this nilpotency, literally got transferred from matrix A over to the product AC. But, and this is the crucial part, that transfer was only possible because they commuted. That condition was the key. And this idea, this principle of how properties are preserved or transferred, is a huge building block in all sorts of advanced fields. So that leaves us with a pretty cool question to chew on, doesn't it? We just saw how one hidden property, commuting, completely dictated the outcome. It makes you wonder, what other secret rules are hiding inside matrices? These things are the engines behind so much of our world, from the computer graphics in a movie to the mind-bending calculations of quantum physics. These invisible structures are all around us, and they show that sometimes the most important thing isn't the objects themselves, but how they relate to each other.